big compound. I'm sorry if you wasted your time finding the molar mass of that compound, because you do not need to know it for this equation. We have 0.00450 moles of aluminum carbonate. Well, 1 mole has how many molecules? I'm sure you all are excited to see Avogadro's number again. Please do remember you need to write molecules out. MOL stands for moles, not molecules. And let's go ahead and report that. Multiplying Avogadro's number by 0.0045, and it turns out to be 2.71 times 10 to the 23rd molecules. Alright, here we go again. We're converting from molecules to moles, so once again, we do not need molar mass, right? Whenever molecules and atoms are involved, or particles, if you hear me say particles, we're talking about Avogadro's number. We have 1 times 10 to the 20 molecules. And how to cancel molecules out? Well, we need molecules on the bottom. We know that Avogadro's number can give us molecules. We know that 6.0 times 10 to the 23rd molecules is 1 mole of molecules. Those bad boys cancel. And that's going to equal 1.66 times 10 to the negative 4th moles. Here we go again. 5 times 10 to the 25th molecules. Avogadro's number on the bottom. And 1 mole on top. Molecules cancel out. And we're left with moles, and more specifically, 83.1 moles. Now, we're going from grams to atoms. When grams are involved in these equations, yes, we do need to find the molar mass. The molar mass of sodium carbonate is 106 grams. Alright, now to set up our equation, we know we have 1 gram. And we know that 1 mole of our compound is equal to 106 grams. So right here, our grams are canceled. We're now in moles. So we now move from moles to atoms, which, when we're going from moles to atoms, we use Avogadro's number is 6.02 to the 23rd atoms. Let's go ahead and check moles. So we're good in atoms. We're where we want to be. Now we just need to divide Avogadro's number by 106, and that gives us 5.68 times 10 to the 21st atoms. Helium. Right, find He on the periodic table. We find that it has a mass of 4 grams. So that's going to be what we're going to use in this equation. Well, we know we have 8 grams of helium, but we know 4 grams of helium is 1 mole. So our units are now in moles. We want to get to atoms. Once again, set the equation up correctly. 1 mole. Our moles cancel out. What we want is going to end up on top, and that's going to be Avogadro's number. And that's going to give us 1.2 times 10 to the 24th atoms. So now for these following two equations, instead of going from grams to particles or atoms, we're now going from particles, so molecules in this instance, to grams. Be careful, we are going to grams, so we do need to find the molar mass of hydrogen, but this is H2, right? So hydrogen's mass number is 1, but we have 2 of those. So 1 times 2 is going to give us our grams, or our molar mass, as 2 grams. Okay? So, let's go. We know we have 1 times 10 to the 23rd molecules. And now let's get out of molecules by dividing by Avogadro's number. And we know that that is 1 mole. Now let's get from moles to grams. So 1 mole is 2 grams. I'm going to cross out molecules, moles. We're now in grams where we want to be. Do the math, which will be 1 times 10 to the 23rd times 2 grams divided by Avogadro's number. And that is going to give us 0.33 grams of hydrogen gas. Here we go. Start off finding our molar mass of our compound, which ends up being 122 grams. Keep that in the bank for a second. We have 1 times 10 to the 24th atoms. And we know Avogadro's number. Of atoms is equal to 1 mole. 1 mole of our compound has a molar mass of 122 grams. We're done. We're done with atoms. We're done with moles. We're into grams. And multiply 122 by 1 times 10 to the 24th atoms. Divide it by 602 hexillion. And we get 202.66 grams. Well, let's go all out. Grams of LPO4. Last but not least, let's look at some percent compositions. Alright. So, first and foremost, we have boron and fluorine. Alright, the mass of boron is 11. Mass of fluorine is 19 grams. Okay, in this compound we only have 1 boron and we have 3 fluorines. That's going to give us 11 grams. It's going to give us 38 grams of fluorine. We're going to add those both together. 49 grams is the molar mass of BF3. Now, from here, to find our percent composition, we're going to say divide our 11 grams of boron into our 49 grams of the compound, and we're going to multiply that by 100, and that is going to give us 22.4% for boron. And same setup, we have 38 grams of fluorine divided by our 49 grams for compound, multiplied by 100, and that is going to give us 77.6% for fluorine. Now, one word of caution for these: if you end up getting 100% when you add up your 2% compositions. So if you go ahead and plug into your calculator and you go 22.4 plus 77.6 equals, that got an even 100%. It is okay if you end up getting 99% or 101%. Alright, that's just us small differences in our math. If you end up going over 102, 103%, or get 97%, your math is incorrect. So always make sure to double check those numbers at the end. Let's do another percent composition problem. We have calcium, we have carbon, we have hydrogen, we have oxygen, and calcium has a mass of 40 grams, carbon is 12, hydrogen is 1, oxygen is 16. We only have, I'll go ahead and write grams in here, we only have 1 calcium. Oh, I'm missing a 2 out here, sorry. So 2 times 2 is 4. 2 times 3 is 6 for hydrogen, and 2 times 2 is 4 oxygen. So that ends up giving us 40 grams, ends up giving us 48 grams of carbon, giving us 6 grams of hydrogen, and 64 grams of oxygen. We add that all up and we end up getting 158 grams for our molar mass of the compound. Now we're just going to go ahead and divide 40 by 158 grams, and by 100, multiplied by 100 is going to give us 25.3%. Okay, continue to do this for all. So 48 divided by 158 times 100 gives us 30.4%. Okay, good. 6 divided by 158 times 100 will give us 5.1%. Last but not least, let's go ahead, 64 by 158 times 100 gives us 40.5%. Almost there, gentlemen. Let's go with iron, fluorine. Iron has a mass of 56 grams.